Imagine you're standing outside on a perfectly clear, crisp night.
Okay.
You tilt your head back, you look up at the stars, and what do you feel?
Usually a sense of scale, you know how small we are.
Yeah, exactly.
Yeah,
You
yeah.
probably feel this sense of endlessness, just infinite possibility.
Right.
You look at that vast, dark expanse, and you think about where humanity might go next. The
Yeah.
moon, Mars, maybe the outer solar
The
system.
final frontier.
Right, the final frontier.
Mhm.
Now, I want you to imagine a sudden physical realization. Imagine realizing that right above you, wrapping tightly around the entire globe, is an invisible, impenetrable ceiling,
A physical barrier.
a locked door. And we are the ones who threw the key away.
It's really the ultimate paradox of the space age. You're staring out at the infinite, completely unaware that you are actually standing inside a cage.
Yeah.
A cage built not of iron bars, but of velocity and shrapnel.
Exactly. So today we're exploring a concept that takes everything we assume about our multiplanetary future and turns it completely upside down. We're talking about the Kessler syndrome.
It's a heavy topic.
It is. And the mission for this conversation is to unpack how human ambition is currently forging our ultimate cage. We're going to look at the hard physics of how space debris is creating an orbital prison that could physically, permanently trap us on Earth.
And to do that, we have to completely reframe how we view the space immediately surrounding our planet. We look at the sky as the ultimate frontier, right? The great open ocean of our time.
Right.
But the mechanics of orbital dynamics dictate that this ocean is rapidly becoming an uncrossable barricade. It's an environment that operates under rules that are completely alien to our day-to-day terrestrial instincts.
I want to start right at the genesis of this concept because when we hear the term Kessler syndrome, I mean, it sounds like something out of a mid-century sci-fi novel.
It does sound very dystopian.
It does. But Donald Kessler wasn't a science fiction writer. He was an astrophysicist at NASA in the 1970s. And what's fascinating to me is that he wasn't even originally studying artificial satellites, was he?
No, he wasn't. Donald Kessler was actually studying the asteroid belt. He was looking at the collisional history of natural celestial bodies, basically the mathematics of how asteroids grind each other down over millions of years.
Because they're just constantly bumping into each other out there.
Exactly. But in the late 1970s, specifically leading up to his seminal 1978 paper, he realized something alarming. He realized that the exact same mathematical models governing asteroid collisions could be applied to the artificial objects we were placing in Earth orbit.
Wow.
And the really scary part was that the timescales were vastly accelerated.
Because we were actively adding mass to the system at an exponential rate. Like an asteroid belt takes billions of years to form. We were doing it in decades.
Precisely. Kessler recognized a threshold effect. In any enclosed orbital system, if you keep adding objects, you eventually reach a critical spatial density.
A tipping point.
Yes, a tipping point where the primary source of new debris is no longer launches from Earth. It becomes random collisions between the objects already in orbit. Once you cross that line, the process becomes self-sustaining.
And this is why it's called ESIM rather than just, a Kessler event or a Kessler problem.
Right.
A syndrome implies a compounding, cascading condition. One failure triggers another, creating this tangled web of interrelated issues. But space is astronomically huge.
It is.
I think the common intuition trap for most people, and I include myself in this sometimes, is trying to wrap our heads around how a few thousand dead satellites can actually block us in. The volume of low Earth orbit, or LEO, is just massive. How does a relatively small amount of mass compromise that much volume?
It's a great question, and it's exactly where human intuition fails us. You were right that the volume is massive. But the threat isn't about the static volume. It's about the intersection of orbital planes over time combined with hypervelocity.
Okay, break that down for me.
Down here on Earth, if you drop a piece of trash, it stays where you dropped it.
Right.
In low Earth orbit, everything is moving at approximately 7.8 kilometers per second. That's roughly 17,500 miles per hour just to maintain altitude and counteract gravity.
Which is just an unfathomable speed, coast to coast in America in, what, a few minutes?
Exactly.
Because an orbit is essentially just falling towards the Earth but moving fast enough sideways that you keep missing the ground.
That is the perfect way to describe it. Now, consider that you have objects orbiting in completely different directions. Some are in equatorial orbits, moving west to east.
Okay.
Some are in polar orbits, moving north to south. When those orbital paths cross, the relative impact velocity can be up to 15 kilometers per second. At those speeds, kinetic energy behaves in ways that are deeply counterintuitive.
Let's actually run the math on that because the kinetic energy equations are terrifying when you look closely at them.
They really are.
Kinetic energy is 1/2 the mass times the velocity squared. Because velocity is squared in that equation, speed is exponentially more destructive than mass.
Right.
So if you have a 1-gram flake of aluminum, literally the weight of a paperclip, and it strikes a satellite at 10 kilometers per second, the energy release is equivalent to dropping a heavy steel safe from the top of a multi-story building.
And we have historical evidence of this exact phenomenon happening.
The space shuttle window, right?
Yes. Back in 1983, during the STS-7 space shuttle mission, a microscopic fleck of paint, something about 0.2 millimeters across, basically a grain of sand, struck the shuttle's front window.
A fleck of paint.
A fleck of paint. It didn't pierce the glass, but it excavated a crater in the fused silica that was incredibly deep. NASA had to replace the entire window pane when the shuttle landed.
Just from paint.
Just from paint. Now I want you to scale that up. Imagine a defunct satellite the size of a school bus, weighing several tons, colliding with a spent rocket stage of equal size.
Which is exactly what brings us to February 10th, 2009. The moment Kessler's theory transitioned from a theoretical white paper to a harsh, undeniable reality, the Iridium-Cosmos collision.
Yes, that was the absolute watershed moment for the orbital debris community. Everything changed that day. You had Iridium-33, which was an active, operational American communications satellite.
Right, providing phone service.
And it collided with Cosmos 2251, a defunct, dead Russian military communications satellite that had been drifting out of control for over a decade. They collided at an altitude of about 789 kilometers, right in the heart of low Earth orbit.
At what speed?
The closing speed was 11.7 kilometers per second.
That is just brutal. And because Cosmos was dead, there was obviously no way to maneuver it. But Iridium was active? It had thrusters? Why didn't they dodge it?
Because the tracking systems at the time simply didn't flag it as a high-probability event.
How does that happen?
Well, the Space Surveillance Network tracks tens of thousands of objects, and they issue these things called conjunction assessments.
Basically warnings that two objects might cross paths.
Exactly. But space is so crowded, and the error margins in tracking are just wide enough that satellite operators receive these warnings constantly.
Oh, I see.
It's an issue of alarm fatigue. If you maneuvered your satellite every single time a warning was issued, you'd run out of the onboard propellant necessary to keep the satellite in its proper orbit. You would effectively kill your own multi-million-dollar asset just by dodging shadows.
So they looked at the data, played the statistical odds, and they lost.
They lost spectacularly. That single collision instantly generated a cloud of over 2,000 pieces of trackable debris.
And when we say trackable, we mean pieces larger than a softball, right? Roughly 10 centimeters or bigger.
Correct. But for every trackable piece, hypervelocity impact models estimate there are hundreds of thousands of smaller, untrackable pieces.
Shrapnel.
Shrapnel ranging from the size of marbles all the way down to microscopic dust.
And because there's almost no atmospheric drag at 800 kilometers up, that debris cloud doesn't just fall back down to Earth.
No, it stays right there.
Over the next few months, orbital mechanics took over. That localized cloud spread out, elongating along the orbital paths until it completely encircled the globe in overlapping rings of shrapnel.
That right there is the essence of the Kessler syndrome, the transition of mass into a higher quantity of smaller, lethal projectiles.
It's a terrifying multiplication.
Cosmos and Iridium went from being two discrete, solid objects that were relatively easy to avoid to a chaotic, swirling storm of hundreds of thousands of untrackable bullets. Every single piece of that shrapnel now has the potential to impact another satellite, creating more debris in a runaway ablation cascade.
So this perfectly frames the architecture of the orbital prison we're talking about today. Let's look at the actual mechanics of low Earth orbit, because LEO isn't just one single uniform place. It's a series of invisible concentric shells stretching from about 160 kilometers up to roughly 2,000 kilometers above the Earth's surface.
Correct. And the danger isn't evenly distributed across those altitudes.
Right.
Below 400 or 500 kilometers, which is roughly where the International Space Station orbits, you still have trace amounts of the Earth's atmosphere. It's a very tenuous exosphere, but it's enough to create aerodynamic drag.
So there's friction.
Yes. Over the course of months or a few years, that drag slows the debris down, lowering its orbit until it burns up in the thicker atmosphere below. We call that self-cleaning.
The atmosphere basically acts as a natural incinerator for the lower orbit.
Exactly. Furthermore, solar activity actually helps us here. During a solar maximum, when the sun is particularly active, it heats up the Earth's atmosphere, causing it to expand upward.
Oh, so the atmosphere literally puffs out.
Yes, it puffs out, and this increases the drag on satellites and debris in those lower altitudes, accelerating that self-cleaning process.
But the real danger zone is higher up, the 600-kilometer to 1,000-kilometer range. This is where the Iridium-Cosmos collision happened. This is where the atmospheric drag is so negligible that an object will stay in orbit for centuries, if not millennia.
And unfortunately, that specific altitude range is prime real estate. It's the sweet spot for Earth observation satellites, weather satellites, and now large-scale communication constellations, specifically sun-synchronous orbits, or SSOs.
Let's define sun-synchronous orbits for the listener, because it perfectly explains why everyone wants to be parked in the exact same spot in the sky.
A sun-synchronous orbit is a type of near-polar orbit. The satellite travels from the North Pole to the South Pole, but its orbital plane precesses it shifts slightly at the exact same rate that the Earth moves around the sun.
Meaning what, practically?
The practical result is that the satellite passes over any given point on the Earth's surface at the exact same local solar time every single day.
So if you are a spy satellite or weather satellite, the shadows on the ground are identical every time you take a picture.
Exactly. It makes it incredibly easy to spot changes. If a shadow is longer today than it was yesterday, you know a new building went up or a missile silo opened.
It is highly advantageous for imaging. But because everyone wants that specific orbital geometry, those specific altitudes are intensely bottlenecked.
Yeah.
It is the orbital equivalent of a one-lane mountain pass. And that is where the architecture of this prison becomes visible. The walls aren't made of concrete. They're formed by these densely packed, overlapping shells of hardware and hypervelocity shrapnel.
And here is where the paradox of this cage gets really profound. Unlike a normal prison where you can walk up and physically touch the bars where you know exactly where the boundary is, this orbital prison is completely invisible to you standing on the ground.
Optical invisibility is maintained.
Right. The stars look exactly the same to us today as they did to the ancient Greeks. You can look right through the bars of your own cage, but the moment you try to launch a rocket through it, you realize the sky is practically boarded up.
It's a massive sensory deception. Our eyes tell us the sky is wide open, but our radar and telemetry tell us the environment is becoming structurally compromised. We rely on the space surveillance network, this global web of phased array radars and optical telescopes, to track these objects.
But as we discussed, they can only see objects larger than about 10 centimeters.
It's like trying to navigate a minefield where you can only see the bowling balls, but the field is actually filled with millions of invisible bullets. And a bullet will kill a satellite just as effectively as a bowling ball.
Which is why spacecraft design has had to adapt to this prison environment. We can't dodge the bullets, so we now armor our satellites using something called Whipple shields.
Invented by Fred Whipple back in the 1940s, it's an incredibly clever piece of engineering. Because instead of just putting a thick piece of armor plating on a spacecraft, which is heavy and incredibly expensive to launch, a Whipple shield uses a thin, sacrificial outer layer of material.
Spaced a few inches away from the main pressure wall of the spacecraft.
Exactly. And the physics behind it are brilliant.
Yeah.
When a piece of micro debris hits that thin outer layer at hypervelocity, what happens?
The kinetic energy is so intense that the debris particle and the impact area of the shield instantly vaporize into a plasma cloud.
It literally melts and shatters the bullet before it hits the main hull.
Yes. That plasma cloud then spreads out over the empty space between the layers, dissipating the impact energy over a much larger area of the inner wall. The inner wall easily absorbs the shock without being penetrated.
It's a fascinating defense mechanism.
It is, but here is the terrifying caveat regarding the Kessler syndrome. Whipple shields only work against debris smaller than about 1 centimeter.
Right. If a 5-centimeter bolt hits a Whipple shield at 10 kilometers per second, it punches straight through the outer layer, straight through the inner layer into the satellite's electronics, and out the other side.
And we know there are hundreds of thousands of those lethal 1 to 10 centimeter objects up there that we cannot track. We only know they exist when an active satellite suddenly stops transmitting and goes completely dead.
And when it goes dead, it becomes a new, tumbling piece of unmanageable mass waiting to be struck by something else.
Exactly.
Which brings us to the grim irony of this entire situation. The culprit. We look at the phrase self-imposed in the context of this orbital prison. We weren't locked in by alien invaders quarantining our planet. We weren't trapped by a freak cosmic phenomenon or a random asteroid shower that clouded our atmosphere. We locked the door ourselves.
It is a textbook example of the tragedy of the commons scaled up to planetary dimensions.
Explain that concept for us.
The tragedy of the commons dictates that in any shared resource system, individual users acting independently according to their own self-interest behave contrary to the common good of all users by depleting or spoiling that resource. Space is the ultimate global commons. No single nation owns low Earth orbit.
So for the last 60-plus years, dating all the way back to Sputnik in 1957, the governing philosophy of spaceflight has been launch, deploy, and forget.
Yes.
It was an era of unchecked, exuberant ambition. We viewed the space around Earth as infinitely vast, assuming it could absorb absolutely anything we put up there.
We built this prison satellite by satellite, all in the name of progress. Every dead satellite, every spent upper stage rocket booster, every explosive bolt and sensor cover was once a symbol of our desire to explore and connect.
But because we focused entirely on the launch and the mission, and almost never on the end-of-life disposal, we inadvertently engineered our way into a corner.
Exactly.
I was looking at the history of spent rocket boosters, and this absolutely blew my mind. For decades, after a multi-stage rocket delivered its payload into orbit, the final upper stage, the massive metal cylinder that actually pushed the satellite into its final position, was just left there,
Just abandoned.
tumbling in orbit. But worse than just being a massive chunk of metal, these upper stages still contained residual, unburned rocket fuel and pressurized gases.
Yes. The lack of passivation is responsible for a massive percentage of the debris up there today.
Passivation meaning rendering it safe.
Right. In the vacuum of space, these spent rocket bodies are subjected to extreme thermal cycling. When they are in direct sunlight, the metal heats up to hundreds of degrees. When they pass into the Earth's shadow, they plunge to hundreds of degrees below zero.
And over years, that thermal stress weakens the internal bulkheads, separating the leftover hypergolic fuels, or the pressurized tanks just fail.
And the result is a spontaneous, catastrophic explosion. No collision required. The rocket body simply detonates from within, turning one large, trackable object into thousands of pieces of shrapnel.
It's a time bomb.
It really is. It took the international aerospace community decades to implement strict passivation protocols, meaning that modern rockets are required to vent all remaining fuel and depressurize their tanks once their mission is complete to prevent these spontaneous explosions.
But the legacy hardware is still up there. We have literally thousands of unpassivated rocket bodies from the 70s, 80s, and 90s acting as ticking time bombs. Some of the most dangerous objects in LEO are the old Soviet SL-8 upper stages.
Oh, absolutely.
They are massive. They cluster at an altitude of around 900 kilometers, that danger zone we talked about, and dozens of them have exploded over the years.
And that's just unintentional debris. We also have to reckon with the intentional creation of orbital shrapnel, the anti-satellite or ASAT tests.
This is where human geopolitical hubris directly accelerates the Kessler syndrome. Let's talk about 2007, the Chinese ASAT test. This is widely considered the single worst debris-generating event in history.
It was a paradigm shift in our understanding of orbital security. In January 2007, China launched a kinetic kill vehicle, essentially a missile without an explosive warhead, relying entirely on the kinetic energy of a direct physical impact to destroy one of their own defunct weather satellites, the Fengjin 1C.
And the Fengjin satellite was orbiting at an altitude of 865 kilometers. Again, right in that critical LEO bottleneck where atmospheric drag is essentially zero.
The impact completely pulverized the 750-kilogram satellite. It created a cloud of over 3,000 pieces of trackable debris and an estimated 150,000 particles larger than 1 centimeter.
Staggering numbers.
Because of the altitude, the vast majority of that debris will remain in orbit for decades, if not centuries. It instantly increased the total tracked space debris population by a staggering 25%. A single geopolitical flex compromised the orbital environment for everyone else.
And the U.S. isn't innocent either. We did an ASAT test in 1985, destroying a satellite called Solwind. But the U.S. deliberately conducted that test at a much lower altitude, around 500 kilometers, specifically so atmospheric drag would pull the debris down relatively quickly.
Right.
But then you have India doing a test in 2019 and Russia conducting a massive ASAT test in 2021, destroying the Cosmos 1408 satellite. And that one was terrifying because it forced the astronauts on the International Space Station to scramble into their escape capsules as the debris cloud passed by.
The ISS incident in 2021 highlights the immediate kinetic threat to human life. It's one thing to lose a weather satellite. It's another to have a multi-billion-dollar habitable station with a crew of international astronauts forced to shelter in place because a cloud of hypervelocity shrapnel is intersecting their orbit every 90 minutes.
So we have the legacy debris, the old rocket bodies, we have the ASAT tests, but now we are entering a totally new era that drastically compounds the math, the era of the mega constellations.
A completely new paradigm.
We are moving from a paradigm of launching a few dozen large, highly reliable satellites a year to launching thousands of mass-produced commercial smallsats.
The shift in orbital architecture over the last 5 years is just staggering. For the entirety of human history leading up to 2019, humanity had launched a cumulative total of about 9,000 satellites.
Total. Since Sputnik.
Total.
Ah.
Today, commercial entities like SpaceX's Starlink, Eutelsat OneWeb, and Amazon's Kuiper project are filing for FCC licenses to launch tens of thousands of satellites into LEO. Starlink alone envisions a constellation of over 42,000 satellites.
Now, to be fair to these operators, they are putting these mega constellations in very low orbits, usually between 300 and 550 kilometers. So if a satellite fails, the atmospheric drag will pull it down and burn it up within a few years. It won't stay there for centuries like the Iridium Cosmos debris.
That is true, and it is a responsible design choice. However, the Kessler syndrome isn't just about the longevity of the debris, it's about the sheer spatial density at any given moment. When you place 10,000 active satellites in a narrow orbital shell, the number of conjunction assessments, those near misses we talked about, skyrockets exponentially.
Because even if a dead satellite burns up in 5 years, 5 years is a really long time for a dead, tumbling object to navigate a shell occupied by 10,000 other hypervelocity targets.
Exactly. The operators rely on automated, AI-driven collision avoidance systems. The satellites actively use their thrusters to dodge each other and trackable debris.
But what happens if something goes wrong? What happens if a massive solar flare knocks out the electronics of 100 satellites simultaneously? Or what if the operators go bankrupt and abandon the constellation?
That's the nightmare scenario. You suddenly have a massive influx of uncontrolled mass and a highly congested regime. The margin for error is shrinking to zero.
Which brings us to the ultimate consequence, the terrifying reality outlined in our mission today. When space debris traps us on Earth. Let's walk through the physical reality of being trapped. What happens if the ablation cascade reaches the point of no return?
If the EO environment becomes fully impassable, it means a hard, uncompromising limit on human physical expansion. It means the closure of launch windows.
Explain that.
Currently, when we launch a rocket, say, a mission to Mars, or a probe to Jupiter mission control, carefully calculates a trajectory that threads the needle through the known trackable debris.
They time the launch down to the second so the rocket slips through the gaps in the orbital minefield.
Exactly. But if the Kessler syndrome runs away, those gaps disappear. The spherical cage of debris becomes so dense that the mathematical probability of a catastrophic collision during the ascent phase becomes a certainty.
And a rocket is fragile.
Extremely. A rocket ascending through LEO is incredibly vulnerable. It is essentially a giant, thin-walled balloon filled with explosive fuel. Even a millimeter-sized piece of debris striking an ascending rocket booster at Mach 10 would trigger a catastrophic loss of vehicle.
So the era of space exploration wouldn't end because we lost the technology or the desire. It would end because the physical doorway out of our atmosphere is structurally compromised.
The barrier to entry simply becomes too violent to cross. We would lose the ability to launch anything. No more planetary rovers, no more space telescopes. But much more devastatingly, we would lose the infrastructure that modern civilization completely relies upon.
This is the part that affects everyone on the ground.
Yes, we lose global GPS, we lose precision agriculture, which relies on satellite timing, we lose global atmospheric monitoring, severely crippling our ability to track hurricanes and climate change. We lose global telecommunications networks.
We basically revert to a 1950s technological baseline, but with a 21st century population size that completely relies on orbital infrastructure to feed and manage itself.
Yes, the socioeconomic collapse following the loss of LEO would be catastrophic.
This brings up the profound psychological impact of the Kessler syndrome. So much of our modern perspective, our culture, our economic models, our science fiction, is built on the foundational idea of a limitless frontier.
Always looking outward.
Right. We have an implicit collective assumption that there is always somewhere else to go. We assume we will eventually mine asteroids for rare earth metals. We assume we will colonize the moon or Mars to ease population pressures or escape planetary disasters. Earth is viewed as a home base.
But a home base implies a temporary state. It implies a harbor from which ships eventually sail. If this orbital prison seals shut, the psychological shift is staggering. Earth transforms from a harbor into a closed system terrarium.
A sealed environment. A terrarium forces us to look inward. If we absolutely cannot go out into the solar system, we are permanently, entirely dependent on the finite resources of the surface of this planet. There is no escape hatch. There is no planet B that we can actually reach.
And that realization changes the entire calculus of human civilization. When a frontier closes permanently, society has to adapt to absolute limits. It forces a reckoning with how we manage the terrarium we are locked inside. Space transforms from a realm of hope and endless expansion into a constant, swirling, visible reminder of our own hubris and our absolute boundaries.
But I don't want to leave this entirely in the realm of inevitable doom. We are engineers. We built the cage. Can we dismantle the bars? What are the actual mitigation and remediation strategies being developed right now? I know the Interagency Space Debris Coordination Committee, the IADC, implemented the 25-year rule.
Yes, the 25-year rule is currently the international standard for mitigation. It states that any satellite launched into LEO must have a plan to safely deorbit itself and burn up in the atmosphere within 25 years of the end of its operational life.
How do they do that?
Most operators do this by reserving a small amount of fuel for a final disposal maneuver that lowers their perigee into the thicker atmosphere.
But the problem with the 25-year rule is that a dead satellite loitering in a crowded orbit for 2.5 decades is still a massive collision risk, which is why the FCC recently updated their rules, demanding a 5-year deorbit timeline for commercial satellites.
Mitigation is essential to stop the bleeding. If we stop leaving trash up there, the rate of increase slows down, but mitigation does not solve the legacy problem.
Right, the stuff that's already there.
It does not remove the thousands of massive Soviet rocket bodies or the millions of pieces of ASAT shrapnel already in orbit. To actually dismantle the cage, we need active debris removal, or ADR.
And this is where the engineering gets absolutely wild. Catching a dead, tumbling, multi-ton object moving at 17,000 miles an hour is one of the hardest orbital mechanics problems imaginable. Can't just set up a robotic arm and grab it.
You really can't, because if the robotic arm rigidly docks with a violently tumbling object, the rotational inertia will tear the arm right off or send the capture vehicle spinning completely out of control.
It's like trying to grab a spinning saw blade.
Exactly. The object is non-cooperative. It doesn't have docking ports, and its center of mass might have shifted over the decades.
So what are the solutions being tested? I know the European Space Agency is funding a mission called Clear Space One, scheduled for the mid-2020s, which aims to use a robotic spacecraft with 4 massive tentacles to essentially hug a piece of debris and pull it down.
That's one approach. We've also seen successful demonstrations from companies like Astroscale testing magnetic capture mechanisms. Another fascinating test was the Remove Debris mission launched from the ISS.
What did they do?
They actually successfully fired a tethered harpoon into a target panel and also deployed a massive net to capture a spinning object.
The net seems like the most robust solution. You match the orbit, stay at a safe distance, fire a massive net over the tumbling rocket body, and once it's entangled, use a tether to drag it down into the atmosphere where both the hunter and the prey burn up together.
It is effective, but it is astronomically expensive. You are launching a dedicated multi-million-dollar spacecraft just to remove one single piece of trash.
Yeah, that doesn't scale well.
At that cost, cleaning up the 3,000 most dangerous legacy objects in LEO would cost hundreds of billions of dollars. Which is why some researchers are looking at ground-based laser ablation.
Wait, shooting lasers at the debris from Earth, doesn't that risk blowing it up into more pieces?
Not if calibrated correctly. The idea isn't to use a high-powered military laser to vaporize the object. The concept uses a lower-powered continuous wave laser.
How does that help?
When the photons hit the leading edge of the debris, they vaporize a microscopic layer of the surface material. That vaporized material expands outward, acting like a tiny, continuous thruster pushing against the debris.
Oh, wow. So you use the laser to create artificial thrust on the object, slowing it down just enough to lower its perigee into the atmosphere.
Precisely. It is entirely contactless. You could theoretically build a laser facility on a mountaintop and systematically slow down thousands of pieces of debris over a few years without ever launching a rocket.
That is brilliant.
But of course, building a ground-based laser capable of precisely targeting orbital assets presents massive geopolitical hurdles.
Because a laser that can deorbit space junk is, by definition, a laser that can deorbit a foreign adversary's spy satellite. It's an ASAT weapon in disguise.
Exactly. The technical solutions exist, but the geopolitical and economic hurdles are immense. The Kessler syndrome isn't just an engineering problem. It's a failure of international law and global cooperation.
Okay, let's take a breath and look at the incredible ground we've covered today. We started with Donald Kessler's astrophysical revelation, realizing that orbital collisions operate on a terrifying exponential curve. We ran the grim math on hypervelocity impacts, where a fleck of paint hits like a dropped safe.
Right.
We analyzed the invisible architecture of this orbital prison, specifically the congested bottlenecks of low Earth orbit. We confronted the tragic irony of the tragedy of the commons, how unpassivated rocket bodies and geopolitical ASAT tests became the bars of our cage. And finally, we faced the ultimate consequence, the prospect of being permanently trapped on Earth, locked inside a terrarium of our own making, reverting to a pre-spaceflight civilization.
This raises one final profound question, something we need to seriously consider if this ablation cascade runs its full, uninterrupted course. We have discussed at length how this orbital prison physically traps our rockets and our human astronauts. The kinetic threat is well established.
Yes.
But if the debris field becomes incredibly dense, grinding itself down over decades into a massive swirling cloud of microscopic metallic dust and highly charged plasma, does it eventually trap our signals too?
Are you suggesting an electromagnetic quarantine?
It is a theoretical endpoint. If the orbital shell becomes dense enough plasma of vaporized aluminum and titanium, it could act like a planetary Faraday cage.
A Faraday cage blocks electromagnetic fields.
Yes. We might not just be building a physical barricade that prevents us from leaving. We might be building a communication blackout that attenuates radio frequencies, ultimately isolating our planet from ever hearing or transmitting signals to the rest of the universe. A totally silent, deafened terrarium.
Wow. Now that is a thought to keep you up at night. A silent, invisible cage built of our own technological hubris. Thank you so much for joining the conversation with us today. Keep looking up, keep marveling at the infinite, but maybe start questioning exactly what it takes to protect the doorway to the stars. Catch you next time.